So, did I push you guys to the limit on the limits assignment? Maybe even past, huh? I don't know. In fact, I pushed you so hard, your life has no continuity anymore. That's what the lesson is for today, continuity. Oh, yes. Pretty bad. My apologies. You guys, we should start with whether you have any questions on that limit stuff. Yes, Darnell? 57? Okay. I'm going to get some pages up here.
Oh, okay, and then 49. I'd rather do 49.
What, they talked you out of that one?
Yeah, I forgot that. I just looked at my notes when we did it last night.
Okay. This is 49 now? I'm a little... What's the page on that? 60? Thanks. 49 on page 60. Okay, I'm finally there. 49. We have the limit as x approaches -2 of x cubed plus 8 over x plus 2. That's 47. Yeah. So 49, I got the limit right, but the numbers are wrong. Gee. I don't know. It's going to take forever at the rate I'm going here. Absolute value of x plus 2 over x plus 2. Does that look correct? Okay. Well, yeah, this is a different one. First of all, you can't do substitution, right? Because if you do substitution, you have division by 0. And yet, there's almost like a cancellation here, isn't there? In fact, I like to think of it this way. See, we don't know if x plus 2 turns out to be negative or positive, do we? Because we don't know what x is. Isn't it, would you agree with me that x plus 2 could be a negative value, and it also could be positive? I mean, I could easily pick one. What if x is -4? Then isn't x plus 2 a negative? Okay, so but my point is, we don't know if it's negative or positive. The numerator will always be positive, correct? So, isn't this just going to be a division problem that comes out 1 or -1? Isn't this really just 1 or -1? Because, I mean, if x plus 2 is a negative, then the absolute value of that's a positive. And then when I divide it by its same negative below, I'm going to get -1. If it's a positive and I divide it by itself, then I'm going to get a positive 1. So it's either 1 or -1. Are you with me?
Yeah.
And
what if it's like, what if the numbers are plus infinity? Like, what if it's not 2? Is it also 1 or 1 or -1 again? Or does it depend on?
Like, if x is 1,000,000.
Yeah.
Okay, then you have 1,000,002 on the top divided by 1,000,002 on the bottom. Isn't that going to be 1? So yeah, even if you get huge numbers or huge negative numbers, shouldn't we wind up at one of those two answers? Okay. Now, when I do that, it doesn't really matter what x is, does it? And so that should be it. My limit should be either 1 or -1. Now, I can't say which it is because we don't know about its sign. But I don't know. I'd be interested how they list that in the back. But they just say it doesn't exist. And I suppose, and here's why. Because, and I should have noticed this. See, when you get really close to -2, then the top's going to get, let's see, when x is greater than negative 2, numbers like negative 1, 0, things like that, then it's going to be positive 1. So you got a graph like this. I see it clearly now. You got a graph. Here's what this thing looks like. And when you graph it, it looks like this. When you get to 2, I'm sorry, negative 2. When you're approaching negative 2 from the right, it's going to look like this. When you're approaching negative 2 from the left, it's going to look like this. And because the left and the right-hand limits don't agree, we'd have to say, yeah. So we got this disagreement thing. So there is no limit, therefore, as x approaches 2. Sorry, took a while to get that one out. Another one. Yes. 65. Use the graphing utility. So did you want me to do it that way with the graphing utility? Well, what do you want? I would say that would make sense because this could be a beast. Sorry. It looks like you can factor the top. You might be able to be done with the other way too. So let's do it with the calculator first. Okay. We've got x cubed plus 4x squared plus x plus 4. So were you having trouble maybe getting the window correct on that? Yeah, that can be a challenge. 2x squared plus 7x minus 4. Okay, there's our function. And the idea is, what's the limit as x approaches negative 4? Okay, well, graphing utility. Okay, function. So we've got numerator x cubed plus 4x squared plus x plus 4 close parentheses divided by denominator 2x squared plus 7x minus 4. So we have something that looks like this. And as x approaches, did I copy that right? So they're asking you when x approaches negative 4. So what's going on over here? Well, whatever this height is, it looks like it's going to be negative 2, but we could check it out probably by doing a trace. And I got to remember, I think this is my trace. And you can't do 4 because it's division by 0. So if you do like 3.99, it gives you a pretty good idea that it's not 2, but it's like negative 1.9-ish. Is that what you were wondering about? So did you have trouble finding the graph with the window on this one, or?
Yeah.
Sometimes, yeah. What can I say? Sometimes that's a tough thing on a TI to try, or one of those graphic calculators, that you're looking through this window and you see nothing and you don't know which direction to go. Sometimes you have to look back and ask yourself things about the domain and things like that. Looks like a window of negative 10 to 10, negative 10 to 10 would have worked here. No? What am I seeing wrong? Is my graph wrong? So you're just getting nothing with a standard window of negative 10 to
It says
10?
window here, window range, and then I put it to 100 and 1,000, just as a straight line through.
So your standard window, let me just see what's, you're sure you have it in here? X cubed plus 4x squared plus x plus 4. Parentheses, 2x. Looks good.
Then I'll change the window to 10.
Do you have both the x and the y windows? Okay, the only thing that's happening is it's trying to connect those two pieces.
Yeah.
But that's about it. That looks good. It looks to me like on a standard window you should get. You got one problem. Graphic calculator is going to try to do up. It's going to try to connect those two things. So a lot of graphic calculators will do this. They'll draw this, and then this will be there'll be like a straight bar connecting these two branches, and you've just got to realize, whoa, the calculator doesn't quite get that. That was a TI, right? Now, do you want to, John, do you want to look at this from an algebra point of view, not just a calculator point of view, or what's that? Okay, I'll be all right. I didn't quite catch what you were saying. All right. Anybody else? Well, we better get going on continuity. Continuity, the fancy name for connected, no gaps. At least, and then we're going to have what? Intervals of continuity. So, I made up a function here. Before you look at the words I wrote, I made up a function that you see in the top right. It's a piecewise function. Do you understand it? Notice brackets, and there's two lines. Top line. When x is not equal to 0, then just use the formula y equals 1 over x. But when x is 0, then then the answer is just 0. Okay, now I've drawn the graph. It's pretty crude, but looks like I had palsy when I drew it. But this is this is supposed to be smooth here. Look at this little. Yeah, looks when I was doing this. So on the other hand, all right. But this one came out pretty good. So, and then you notice at 0, I've indicated this by putting a dot there. So this is kind of a weird function, but it's got almost got 3 chunks. Chunk 1, chunk 2, chunk 3. Okay. Now let's look at the rules. So this thing jumps around and is in pieces. So guess what? We got a continuity problem. Here are the 3 requirements for continuity. You got to have the function to, if I want to know if it's continuous at point C, then you can't have it undefined. Well, I've gotten around that by doing this. If this would have just been like this, y equals 1 over x, this would have failed right away because there's no value at 0, because 1 over 0 is meaningless. But I got around that, a little bit of a cheat, by saying, if it's at 0, then the answer is this. So I got over part 1. F of 0 is defined on mine. It's 0. But now, number 2, the limit as f of x approaches c exists. Okay? As x approaches 0 from the left, what's the limit of this function? Negative infinity. As x approaches 0 from the right, What's the limit of this? And obviously they don't agree, so does the limit of f of x exist? No, it fails test 2. And test 3 says the limit has to equal the number. I need to, I need another example to show you step 3. So I'm going to make another one up here. Okay, this time, here, we'll make this function up. So I'll just do it by drawing a graph. Here's another piecewise function. Okay, it's obviously in, I guess you could say, 3 pieces again. But it looks like a straight line, with the exception that we have a hole right here, and there's still a point at the value of x equals -1, but it's in a different place. So the problem here is the left-hand limit of this function, as x approaches -1, is 1. The right-hand limit, as x approaches -1 from the right, is also 1. So the two agree, but Rule 3 says this limit, which both agree on is 1, does not equal the actual f of -1. So in other words, even though these two agree, do those two agree with what that value of that function is at x equals -1, and they don't. So you can't have kind of a point in exile like that either. And so, just going back, that's what Rule 3 is saying. Rule 3 is saying, when you take the limit as x approaches something, is it equal to the actual value of the function at that number? And it was not in that other example. We say if f is continuous at every point in an interval, then it's continuous on that interval. So on this one, you could say this function is continuous on the interval and on so I mean it's continuous everywhere else. So we can define intervals of continuity. So it's perfectly okay from -∞ to -1. It's perfectly okay from -1 going on forever. We just have that one problem that's discontinuous. I should say that. It's discontinuous at, okay. So we got kind of our notation down. Okay, now open your books up. Let's just look at a few in here. On page 62, example 1, we've got some functions, and they're drawn for you. They're plotted for you. Okay, what do you, just by looking at the function and looking at the graph, do we have any problem with continuity? And especially look at the equations. The equations are above. What are key things to look for in continuity? You know, what caused y equals 1 over x to cause a problem? The thing that really got us in trouble is the domain, because x cannot be 0. Whenever you have a domain issue like that, that means we're going to have a break. and we're going to have a continuity problem. So number 1, our number 1A in example 1, I finally got it right, is just a good old parabola. That has no continuity problem. So we would say that's continuous on the interval negative infinity, comma, positive infinity. Same with the one on the right, the cubic function, right? There's no problem there. Now go to the next page. The first one there, that's the one we were doing in class. That has a continuity problem, right? No way can we do anything in 0. So we would say what? That's continuous on negative infinity to 0, open parenthesis, because it never gets to 0. And it's continuous on 0, comma, positive infinity. Okay, then we got one of these guys with a hole in it. And why do we have a hole in it? Look at the equation on that middle one on page 63. Why do we have a hole there? Because of domain x cannot equal 1. So what do we say about continuity? Well, it's not continuous at x equals 1, but it is continuous on negative infinity, comma 1, and 1, comma positive infinity. And then look at the far right one. How about continuity on that one? Be careful. Check out the domain. I mean, you don't have to be any more careful than that. Do we have to worry about 0 in the denominator on that one? And the reason we don't is there's no way that denominator can be 0. Is there? I mean, how could x squared ever be negative 1? It can't. So, unless we're in the complex numbers. So, we're okay here, and that's continuous on everything. Okay? Let's look at page 64 now. Continuity on a closed interval. Let's see, what are we talking about here? Well, just that. If you look at the parabola lower down in the margin on page 64, that's f of x equals the principal square root of 3 minus x. What do you get? Half of a parabola. And we would say that looks to be continuous on the closed interval. At least it's half closed. 3 square bracket. Well, negative infinity, comma, 3 square bracket. Why? Because it does include 0.3. See, before, when we were doing some of these things with an open dot, we always had to use a rounded parenthesis to indicate not included. But here, yeah, there's a point at the end, at the vertex of a parabola. It's continuous there. Okay, so we have that situation. Interesting. What are they doing there? I want to look at example 4, but I'm a little bit puzzled by their graph. So I'll just do a graph up here. Okay. So the first function is 5 minus x. And we only want to do that from what? From negative 1 to 2. And what do we have? Equal signs on both ends? Yes. So okay, so there's that part. So it's only a line segment because the book said only do it between these 2 points. Okay, now what's the other one is the curve x squared minus 1. I should change colors here. Okay, x squared minus 1. And we're supposed to do that from 2 not inclusive to 3 inclusive. From 2 to 3 The end point we want to be solid, but this part we want to be open. Yeah. Only problem is it kind of, I see, that is curved. I was puzzled by why it looked so straight in the book, but it's because we're on such a small piece of it. Okay. So the only thing that I don't like about this is it doesn't show the red dot anymore. The open circle kind of covered it up, but it's really there. Okay. So now, what about the continuity? If that red dot is really there, like it should be, doesn't the red dot kind of fill up the open blue circle? It should. And I can't draw on it to show you that. So, what about the continuity? We don't have an issue. This is continuity on a closed interval from -1 through 3. Because that red dot's supposed to be showing there. This is all, right? That's all closed up. If I just get rid of the curve, see the red dot's really there. When I put this there, the red dot should still be filling that. Okay. So that's okay. So sometimes you can have piecewise function that fits perfectly together and creates a nice closed interval. Now look at the bottom of the page and you see a classic discontinuous situation, the greatest integer function. You remember them as otherwise called a step function? And every time we have to jump up to a new step, I hate to say it, but we have discontinuity. Of course, the problem here is the left-hand limits and the right-hand limits never agree. So this is kind of a mess. What we could say is each stair tread is what? A short section of continuity. So we could say that that stair tread that's sitting on the x-axis has what continuity? From square bracket 0, comma, open bracket 1, right? Open bracket 1, because when you get to 1, it's empty, pops up. And then you could just, each stair tread could be its own little interval of continuity. So unfortunately, you got tons of discontinuity there. Okay. So I guess let's look at some problems on the assignment. Page 69. First section, 1 through 10. Determine whether the function is continuous on the entire real line. Explain your reasoning. Okay. Let's take some evens here. How about number 2? What do you think? Any points of discontinuity there? What do you look for to try to detect points of discontinuity? What do you examine to find discontinuity? I thought I got that across today, but it is very silent in here right now. Domain, right? In other words, just look, is there any x you can't plug into that equation in number 2? No. You know, what are the big no-nos? You can't have division by 0, and you can't have a square root of a negative. And if it's a word problem, you might have some issues, but we don't have a word problem. Do we have a denominator? No. Do we have a root? No. Is there anything you can't plug in for x? No. So that's continuous, negative infinity to infinity. How about number 4? I heard 3 mentioned, and I should hear a little bit more mentioned. Yeah, there's actually 2 values there that would create a problem, right? 3 and -3. So there are 2 points of discontinuity. So if I asked you to write out continuity for that, you would actually have to break it into 3 chunks, wouldn't you? Negative infinity up to -3, -3 to 3, 3 to infinity. You could break it up like that. How about number 8? Well, I don't want you to do it right now, but what should you be thinking about on number 8? Thought process. Well, what's the danger? that there could be a 0 in that denominator, right? What's the best way to detect? Well, I shouldn't say the best, but what's one real handy way to detect if that denominator could be 0? And what would you, set it equal to 0 and see if you can find out when. And going on, what are some cool ways that might allow you to do that quickly? Yeah, see if you can factor it. That's a big one. Let's see, can that one be factored? Sure, isn't that x minus 5, x minus 1? Which tells you which two values of x can you not have. Isn't it 5 and 1? So now, again, we have two, so cool. And if you can't factor it, well, then you could complete the square, use the quadratic. How about 10? Number 10. 4 and negative 4 are problems? Okay. They didn't have any roots there. It's kind of surprising. But again, always look for the bad boys, the roots of negatives and the division by 0. Next section, 11 through whatever. Describe the intervals. So just by vision, so let's just take a few of these. What are the intervals of continuity on number 12? The graph for that one is there. Give me all the intervals of continuity. Give me one of the intervals of continuity. Yeah, and that, what kind of parenthesis on the negative 2? Right, rounded or open. Good. Next interval of continuity on number 12? Negative 2 to 2. You project your voice really well. I could have sworn you were over there. How about another one for number 12, the last one? 2 comma infinity, right? About 21? No, that's not. Tell me about 21. Can you factor it? Here's that factoring again. Negative 5 and negative 4, it works. X minus 5, x minus 4. And so what two values of x can x not be? 5 and 4. And so you wind up with 3 intervals again. The factoring just keeps coming back. Why did we spend time on factoring? That's why. Next page. 24. Well, just look at the graph. Obviously, we got some problems here with continuity. Wherever there's a jump, but you could list them separately, right? Okay. Let's look at one. Let's take one like 26. Now, even without drawing the graph, let's think about this just a minute. 26. Tell me a little bit. What does that mean when you have two lines like that? Piecewise, right? Two pieces. The top piece is, of course, a line. The bottom one is a parabola. But one issue is, what happens at 2? Do they whiff or don't they? Well, real quickly, check it out. What is the top one when x is 2? It would be 5, right? And what would the bottom one be if it could be 2? Wouldn't it also be 5? And you notice how it's included, the point is included on the top but not on the bottom? So isn't this one of those where we have this open dot on the one on the bottom and the one on the top, so nicely fills it in? And so these two work beautifully together. See that? And you can tell it fairly quickly by looking at the endpoint. So anyway, next section, 35 to 38, says discuss the continuity. If there are any discontinuities, determine whether they are removable. Yeah, I didn't tell you what that was, so we better go back and look at that. I did, but I just didn't give it a name. That, you know that one I had where, well, here, we'll just show you. I thought, where do they have it? Bottom of page 63. Consider an open interval I that contains a real number c. If the function f is defined on I, except that possibly c, and f is not continuous at c, then f is said to have a discontinuity. Discontinuities fall into two categories, removable and non-removable. A discontinuity at c is called removable if f can be made continuous by appropriately defining or redefining f of c. So, you know, like, for example, look at this one right here. On the same page, this line with just an open dot, that's a removable discontinuity, because if we just said, made it a piecewise and said, oh, wait a minute, f of 1 is 2, that would kind of fill it up, and it would be okay. So that's called a removable discontinuity. And then, this one obviously not, because here we have a discontinuity at 0. So if I just say, oh, f of 0 is 0, that won't do it because it's still disjointed into three parts. So removable discontinuity, non-removable. Okay. Back to the assignment. I guess that's pretty much the theme. I think we're ready to go. I should look up at what the assignment is. Has anyone done that already? Let's look. This is 1.6, right? 1 to 45 odds plus 65. And, okay, let me just reaffirm what's happening. And since this is our last section, here's the way I deal with getting ready for a chapter test. Tomorrow, tomorrow's our one day off, right? So our next class on Wednesday, questions, we'll begin with questions on 1.6, and we'll have what I call review 1. So we'll let you ask questions about this assignment, and then in place of a new lesson, we'll start talking about issues about a test on chapter 1. Then I will have one more review day on Thursday, leaving us with the real test on Friday. And I think that's consistent with what I've already told you, but that's where we're headed for our schedule. Okay, so the theme this week is definitely test. There's several things at the end of a chapter here. I'm not going to formally assign these, but these are all things you can look at. There's an algebra review, just in case you still feel like you need to firm some of those things up. There's a chapter 1 summary and study strategies. Pretty nice of them to do. There's chapter 1 review exercises. And so those together are all pretty good ideas to help you at least start getting ready for the test. So any of those are game for questions. Now, please don't just sit there. I really need you to take an active role after, I mean, tomorrow, for the 2 review days, I would like it kind of be directed by you. So ideally, and usually this isn't very hard, we have 4 or 5 good questions that'll easily probably keep us busy. You know, somebody might say, yeah, could you go over that section on, a little unclear on it, or I didn't understand the review question in the book, number 72, could you go through, you know, whatever. So I'd like to do it that way. If you don't pick anything, I certainly got stuff to do, but I'd rather go right at the things you would like. Okay, I guess I'll just let you go early today. Thanks.